At this point, if we had the forces and accelerations at the same slopes, we could have plotted a force versus acceleration graph. However, since the forces and the accelerations were measured in different slopes, we have to take these models of force versus ramp slope and acceleration versus ramp slope and infer what the relationship is between force and acceleration. The force relationship, remember, we had a slope of 5 newtons times ramp slope and a very small number indicating that the ramp almost went through the origin but not quite. This is a small constant due mainly to friction. We call the constant here C1 and we'll call the constant here C2. Both of these are relatively small constants. Remember that for our best fit here it was 0.05 meters per second squared when we had a slope of 5.94 meters per second squared. So it really is small compared to this, but it does indicate friction. I'll note also that this experiment was done using a low friction dynamics cart and not one of the toy cars. That's not going to make a whole lot of difference in the end result, but it does allow us to be a little bit more accurate here, and the values of C1 and C2 that we would get with the cars would be much greater than they are with the low friction carts. However, those constants aren't going to make a whole lot of difference because we're going to forget about them. We're going to say, okay, these constants are small and all they do is raise the graph or lower it. We're really interested in how the slope of this graph and the slope of this graph compare. So we write these two equations, just omitting the C1 and C2. We're fudging just a little bit here, but we don't want to get too mathematically demanding at this part of the course, and we don't want to get into a lot of interpretation of these quantities. When we eliminate ramp slope between the two equations, let's say we solve this equation for ramp slope, we get ramp slope equals A over 5.94 meters per second squared. Substitute that in here and simplify. We get a force of 0.84 newtons divided by meters per second squared multiplied by the acceleration. Now it's going to turn out that that number should actually be the mass of the dynamics cart in kilograms. It isn't, because the 5.94 meters per second squared is incorrect. Again, I believe because the slopes were incorrectly calculated. Had the slopes been calculated correctly, using the 61 centimeters instead of the 43, this number would have been closer to 9 meters per second squared, which is within 10% or so of the accepted value of 9.8 meters per second squared, which is the acceleration of gravity. We'll see later exactly why this should be equal to the acceleration of gravity, but for now, let's accept the fact that it should. That would change the force here. It would actually have been about 5.5 units here, or 0.55, and actually the mass of the cart is right around 0.5 kilograms, so things would have worked out.